Okay. So the bulk of what we're going to talk about today are substitution methods, which means that we're going to find clever ways of transforming differential equations that we would have otherwise no idea to solve into a form that we already know how to solve. So far we know how to do direct integration, we know how to do separation of variables, we know how to use the integrating factor method. So these are the tools that we have in our hands. And when you have a hammer, everything looks like a nail, right? So we want to try and make sure that we can transform these equations into the form that we can apply our methods to. Okay? And I kind of whet your appetite with this almost linear ODE. It's a non-linear, right? But it looks linear, so we'll start with that. So consider y dx plus q of xy equals h of x y to the n. Okay. And the idea was that I pointed out was that if you, for a moment, ignore this y to the n term, we have a linear ODE. Okay. So specifically when n is 0, we have a linear ODE. If n is 1, we still have a linear ODE because I can move this to that side and then just factor out the y. Okay. But when n is neither 0 or 1, then this is non-linear. Right. So the question becomes, can we transform this into a linear ODE? Can we make this linear by changing the variables?
Is that y of x?
X, y, q, y. Is that it? Okay. Alright, so since this is a problem child, we're going to begin by dividing through by y to the n. Okay, because we want to wish it away. Right. So we have 1 over y to the n dy dx plus q of x y over y to the n is h of x. So by doing this, I'm implicitly assuming that my function does not vanish. Okay, at some point, otherwise this would be a very deadly move. Okay. Alright, so rewriting this is y to the minus n dy dx plus q of x y to the 1 minus n equals h of x. Okay. So things are looking somewhat brighter because we have gotten rid of this nonlinear term from that side, but now we have an expression here that is still nonlinear. And so the idea is that can we set this expression to be a new variable and hope that the resulting change of variable will lead to a linear ODE. So in other words, all this junk here we're going to call something new, v. So we are going to set v to be y to the 1 minus n. And our hope is that we can then transform this equation to look like dv dx plus, it will no longer be q, maybe a new function, let's call it q naught of x, v equals h naught of x. This is what we are hoping for. So that now we can apply integrated factor method to solve this. Okay, so we're going to play around with this change of variable and see whether we can get something like that. Okay, so if we set this guy to v, then somehow we need to get the v dx into the picture. Okay, so we need to replace the y dx by some derivative involving. So if this is true, then my y is v to the 1 over 1 minus n. Yes?
Why do you have zeros now as subscripts?
Because the coefficient need not be the same as that. It could just be a different function of x. I don't expect that if I do the change of variable that I'll still have this coefficient the same. I could have some factors of x multiplying it, but I don't care, as long as it's a function of x. Right? That's what we care about. And the same thing for the h. Could be something different. Okay, so hopefully this will be a little easier to differentiate. Now if I differentiate this, I get dy dx, and then hopefully I can get an expression dv dx from here that I can solve and then make a replacement for the y dx. And so, what is dy dx here? If we use the power rule, this is 1 over 1 minus n, v to the 1 over 1 minus n minus 1 times dv dx. Yeah? And then if you just simplify this 1 over 1 minus n minus 1, we have dy dx. That's 1 over 1 minus n, v to the n over 1 minus n, dv dx. This is a chain rule. Okay, so I have my dv dx in here, and now this can replace dy dx in my previous equation. Let's call this that. So now I have y to the minus n times 1 over 1 minus n, v to the n over 1 minus n, dv dx, plus q of x. Now this guy is v, so we put v here, is h of x. Okay, but we know what y is. This is y. Y is v to the power 1 over 1 minus n. So I'm going to replace that. So this is v to the power 1 over 1 minus n to the power minus n times 1 over 1 minus n, v to the n over 1 minus n, dv dx, plus q of x, v equals h of x. Something wonderful is about to happen. Clearly, this is v to the minus n over 1 minus n. If I bring out the 1 over 1 minus n, this is times v n over 1 minus n, dv dx, plus q of x v equals h of x. Yes? And now what is this? It's 1. So what do I have? 1 over 1 minus n dv dx plus q of x v is now h of x. And if I want this coefficient to be 1, I just multiply through by 1 over n, so that I have dv dx plus 1 over n q of x v equals 1 minus n h of x. And now this is linear in terms of v. Okay. So notice that my coefficient is no longer q of x, it's a constant times q of x. But that's fine. I can still apply my integrating factor. And then my right hand side is not just h of x, it's a constant times h of x. That's also fine. Yes?
So how can you know that something so complex would work out so nicely?
Because somebody did a million tries and figured out this works. I didn't come up with this.
No, but like
But then the goal is so the spirit of the whole method is that this is what you want. Okay, this is what you don't want. So we try and eliminate it, and then we're like, what happens if I set this to a variable v? You don't know ahead of time that this is going to work. Whoever developed this method didn't know ahead of time that this was going to work. You tried something. And then you found out that, oh, it works. And that's how research in mathematics happens. That you're never certain that your idea is going to work. You just try it. You try it, if it doesn't work, you try something else, you try something else. But then you know what you want. So you keep your goal in mind. And you keep trying until you get something that way. And in this case, this substitution works for us. Okay, so it's not as easy as I made it look. It took a lot of attempts. And then finally, oh, this one works. Okay, so this is it. And anytime we have a differential equation of this form, if we make this change of variable, we are guaranteed to convert it into a linear differential equation. Now, of course, once you solve this for v, finding y is trivial because you can just come back here and find y because of the change of variable. So if you have v, you have y, and then you have the solution to your differential equation. Does that make sense? Okay. So equations of this form, where n is not 0 or 1, are called Bernoulli. And this is how we can solve it. So here my n is not 0 and it's not 1. It's something else, some other real number. Okay. So we'll take an example. This is the definition 1 in your notes. Yeah, I keep bringing a new eraser, and someone keeps picking it up. So I'm going to buy one for myself, keep it in my bag, so that nobody can take it. Alright. So example 2. Solve the differential equation x dy dx plus 6y equals 3xy 4. Okay. Now if I divide through by x, I have dy dx plus 6 over xy equals 3y to the 4th. So this is clearly Bernoulli. Because my n is different from 0 or 1. Okay, now, of course, this is non-linear, so you wouldn't be able to even do the integrating factor at this point in time. So we'll proceed, and we'll set v to be y1 minus n. Here, my n is 4 over 3. Okay, and then this is y. 1 minus 1 over 3. And so my y is v to the minus 3. So we'll go through the process. Dy dx is minus 3v minus 4 dv dx. You don't have to memorize anything, you just have to remember your substitution. Okay. And you don't even have to memorize the substitution, just divide through by this term here and the substitution will come out. So you don't have to memorize what the substitution is. Right? What I mean is that if I just divide through by this, I have y to the minus 4/3 dy dx plus 6 over x y to the minus 1/3 equals 3, and this will be my v. So all you have to do is divide through by the nonlinear y term, and then you can get your v immediately. Okay? Alright, so we replace now my dy dx by this expression. And so we have y to the minus 4/3 minus 3b minus 4 dv dx plus 6 over x v equals 3. Now, of course, this is v to the fourth power. So minus 3 out. V to the minus 4 v dx plus 6 over x v equals 3. So here I've used the fact that y to the minus 4/3 is y to the minus 1/3 raised to the fourth power, and this is v by my substitution. Okay. Okay. So this guy conveniently becomes 1, and then we have minus 3 v dx plus 6 over x v is 3. Divide through by 3, or minus 3, you have dv dx minus 2 over x v is minus 1. And now this is a linear differential equation in terms of v. Okay. So applying integrating factor. What will be the expression for my integrating factor? What is my q of x? Negative 2 over x. So this is e integral minus 2 over x dx. You cannot forget that part. And so this is e minus 2 integral 1 over x dx. This is e minus 2 natural log of absolute value of x. We don't care about the constant. And this simplifies to x squared. X to the, so 1 over x squared, right? Because this is e to the ln of absolute value of x to the minus 2, and then we get 1 over x squared. Alright, so now that we have an integrating factor, what do we do? What do we do with the integrating factor? Yes? What do we do with this guy? Yes? Oh, it's on and up?
No,
Okay.
no.
What do we do with this?
I was just wondering, because this is the example 3 in the lecture notes. You wrote down this example.
Yeah, I didn't update the notes, so I moved the Bernoulli equations first. So just go according to what the notes actually have said. This example 3, keep it as example 3. I just realized that I didn't update the notes online. Okay, what do we do with 1 over x squared? Yes?
Do you multiply it?
Multiply through the equation by 1 over x squared. Because we are trying to make this integral. So we are multiplying through this equation. We have 1 over x squared v dx minus 1 over x squared 2 over x v equals minus 1 over x squared. So we have 1 over x squared v dx minus 2 over x cubed v equals minus 1 over x squared. And if everything works out right, we expect my left-hand side to be the same as my integrating factor times my unknown function. And you can check. Right. You differentiate v, you get this part. Differentiate x, you get that. And so if I integrate both sides with respect to x, then I have 1 over x squared v is what? So is it minus 1 over x plus c? Because it's x to the minus 2, we increase the power by 1, we get x to the minus 1, so this is plus. And so my v of x is now x plus cx squared. Am I done? Is this my solution? Why not? I just found a nice quadratic function that,
Do you have a substitution back there?
yeah, this solves that differential equation, not this differential equation. Okay. So I have to use my substitution to get y. I know that my y of x is v to the minus 3, and so my v is x plus cx squared to the minus 3, which is 1 over x plus cx squared. Okay. So of course it's important that x is not 0 for this to really make sense. And so we have found a general solution to our differential equation. Yes?
What is the symbol between the two integrals?
This?
Yeah.
Oh, that's the differential. I'm integrating with respect to x. Yes.
And that's the solution to what differential equation?
The solution to this differential equation. Because we went from this to that. This is non-linear, we made it linear, we solved the linear problem, and then we used our change of variable to get the solution to the non-linear problem. This is how substitution methods work. Any other questions? So just take this in. A lot of things to keep track of. Make sure that you're on the right path. But if you follow the idea, you don't have to memorize anything. Just recognize that, put your differential equation in that form. This guy, you don't want, divide through by that, and then the coefficient of y, whatever y becomes, is what you change the variable to. Because sometimes it's like, is it y? I have students get confused on exam. Is it y to the 1 minus n or y to the n minus 1? And you don't need to know that. Just divide and it will be clear. Okay. All right. Unfortunately, this is the only example. All right. So you have some of these in your practice problems. Just try them out. Alright, let's look at some other substitution methods. So this was example 3 in the old alright. Let's say other substitution method. So generally, where the x it is f of xy. So we're going to assume, for the first case, assume that f of xy is a composition. It's a composition of some function f and a linear function ax plus by plus c. This will be a function of x and y. Okay. So if we assume that my f of x has this form, there is a natural substitution that can be used to solve the differential equation. Of course, this is not separable. It's not depending on what f is, it may not be linear. Okay, so we can use directly any of the methods that we do. So we are looking at this differential equation. Big F of AX plus BY plus C. Can we make this either linear or separable? The idea is to make a change of variable with the inner function of your f. So you set v to be ax plus by plus c. Why? Because if this is strictly a function of v, and I somehow get my derivative to be a function of v, what happens? What can I use to solve this? If this is strictly a function of v, right, and my derivative is in terms of v, what method can I use to solve this?
With the dx on one side.
Yes, separation of variables. Right? You have the v over f of v is dx. It's just separated, and then you can integrate both sides and solve. So that's the reason for making this change of variable. Because we would like to eliminate the x and y dependence of the function into just a single dependence. And of course, once we do that, we have to change the derivative as well. Alright, so let's see how the v dx looks like. So this is a plus b dy dx. Of course, c is constant, so it vanishes. And so my dy dx is really dv dx minus a times 1 over b. Alright, if I replace this here, I have 1 over b dv dx minus a equals the function of just b. So I'm getting closer. And then finally, if I want to isolate the vdx on that side, I just solve for the vdx. So my vdx is going to be a plus b f of v. And so this is a function just of v. A is a constant. So if I separate variables, I have dv over a plus b f of v equals dx. And then if this is integrable, I can integrate both sides with respect to this side with respect to v, that side with respect to x, and so on. So hopefully this leads me to some v of x, which I can then use to find y of x because of my change of variable here. That's the idea. So this function could be, for example, e to the ax plus by plus c. That's a composition. It could be the sine of ax plus by plus c. That's also a composition. That's what this capital F means. So in this case, the capital F is the exponential function. In this case, the capital F is a sine function. And then the argument is a linear function of x and y. That's what this notation is. So that right-hand side could be anything. It could be just a power function, ax plus by plus c to the 1/2. So in this case, my f is just some function to the 1/2 law. Okay, but in all those cases, we're going to use the argument or the inner function as our change of variable because of what we want to have. Yes? All right. So let's take an example. This is example 1 in your notes. In the lecture, this will be example 2. equals x plus y plus 3 all squared. How would you characterize this differential equation? Is it linear? Why is it not linear? Because you're going to get y squared if you expand that sign, right? So this is not linear. But it's first order. Is it separable? No, at the moment. Right? You cannot separate this into a function just of x and a function just of y. Okay. So applying this idea, we're going to think of this as a composition of this linear function x plus y plus 3 and some function to the square power. And just set this to be our v. So we're going to set v to be x plus y plus 3. And then we have to make a change of variable for the derivative. So dv dx is 1 plus dy dx, which implies that dy dx is dv dx minus 1. So I take this, replace my left-hand side, and now I have dv dx minus 1 equals v squared. And so I have dv dx equals v squared plus 1. Right. Now this is a function just in terms of v, and I can separate variables. So I have 1 over v squared plus 1, dv is dx. Hopefully, this guy has an antiderivative. Does it? Yes, what is it? The arctan. Okay. So this is the arc tangent of v equals x plus some constants, which means that my v is the tangent of x plus c. Wow. I have solved the separable equation, but I am yet to solve my original nonlinear equation. Okay, how do I get a solution for my original equation? I use the change of variable. So just replacing this with my solution for v, I have the tangent of x plus c equals x plus y plus 3. And I can solve this for y. Right, so my y of x is the tangent of x plus c minus x minus 3. And now I have a general solution for my original nonlinear equation. Any questions? Okay. Now remember how the tangent looks like. You have these planes bounded by asymptotes. And so depending on your initial condition, they're going to lie within one of those planes. You cannot extend beyond it. Right? So you have minus pi over 2 and pi over 2 and so on and so forth. Okay. So when you are given an initial value problem, you have to be careful when choosing what the domain of this function will be. You have to use the fact that the tangent has these vertical asymptotes or scattered and multiple. Right? Any questions? All right. So this type of differential equation leads us to a separable equation. Right, we're going to take another kind that we can also solve by substitution and see what that leads us to. Yes.
On the solution, where does the v squared come from?
Sorry?
On the solution, where does the v squared come from? Right, yeah, right there.
Remember, That's our f. It's a composition of something squared and this linear function x plus y cubed. So when you set this to be v, this is now v
Okay.
inside here.
Okay.
That's why we have this.
Okay, sir. Thank you so much.
Any other questions? Okay. All right, now the second kind of nonlinearity that can arise is if my, so again, this is f of xy, and this is case 2. If f of xy is a composition of some function f and x over y. Okay, what do we do? Let's see, it's actually more convenient doing this. It's a line. And again, if we set v to be y by x, then we would have transformed this into hopefully some dv dx in some function of v, is the idea. Where this could be, there could be some constant or expression multiplied by v. But this is the idea that if we replace this by v, then hopefully we can get, and the change of variable can allow us to transform this y dx into something involving v dx, that we could get something that's similar. Okay. All right. Now, if we make this change of variable, then my y is v times x, and my dy dx. If we think about v as being a function of x, then this is v plus x dv dx. Okay, if I just use the chain rule. And then we can send that over there. So replace my dy dx with v plus x dv dx. And this is supposed to be some f of v. So now we have x dv dx is f of v plus v or minus v. And then on this side we have a function just in terms of v. And so hopefully we can find an antiderivative for this. And so now we have been able to separate them out. We can integrate both sides and then find out what v should be. So that's the idea here. Yeah. Okay. Now, of course, if you had done x over y, derivatives are a little bit clumsier. That's why y over x is more convenient. All right. So example 2. This is example 3 here, but it's example 2 in your notes. We have 2xy dy x is 4 x squared plus 3y squared. Can we write this in the form dy dx is some function of y over x? Right? We can. If we divide through by this coefficient here, dy dx is 4x squared plus 3y squared over 2xy. So that simplifies to, we have 2x over y plus 3 over 2y over x. Now there appears to be a problem because here I have a constant times x over y and a constant times y by x. I want to write this as a composition involving y by x. And so how can I do that here? Yes?
You do y over x to the negative 1.
Yeah, reciprocal. So we can just write this as 2 over y over x, problem solved. Plus 3 over 2 y over x, like this. So that now if we set v to be y over x, then my right hand side looks like 2 over v plus 3 over 2v. So it's just a function in terms of v. Alright, so at least this part is done. We've been able to write this in terms of v. We work out the derivative. So we know that y is vx. We want a substitution for dy dx. So this is what v plus x dv dx. We throw that back into the right hand side or left hand side. We have v plus x dv dx equals 2 over v plus 3 over 2v. So then we isolate dv dx. I'll take this one at a time. So this is x dv dx. We send v to the other side. We have 2 over v plus 3 over 2v minus v. And this gives us 1/2. And then we can separate. Right? That's a function involving v. So we can have 1 over 2 over v plus 1 over 2v. dv is 1 over x dx. Now, in this form, the antiderivative is not so obvious, but if you combine the fractions, you're going to get a clue as to what the antiderivative would be. So this is what 2 over v plus v over 2. So this is 2v. What do we have here? We have 4, right? Plus 4 plus 4. V squared, right?
Yeah.
Okay. And so my left hand side is going to be 2v over 4 plus v squared dv equals 1 over x dx. Now we can find the antiderivative of that side using u substitution. We set u to be v plus 4 plus v squared. The derivative gives you 2v. Okay, and then you can solve this. So I'll leave you to fill in those details. So on this side, set u to be 4 plus v squared. U is 2v V, dV, and then you can just pick your change of variable. So this side is just 1 over u du is the natural log of the absolute value of x plus c. Okay. And of course, this is the natural log of u is the natural log of the absolute value of x plus c. So what is u? It's that. So this is the natural log of 4 plus v squared, natural log of absolute value of x plus c. If we think of our constant as a natural log of some constant, then we can combine this side of the expression and say that this is the natural log of 4 plus b squared equals natural log of cx by using the sum rule of the law. Right. Okay, so now we are solving a logarithmic equation. This side we know is always going to be positive because it's 4 plus b squared. And this is the natural log of the absolute value of cx. And so clearly 4 plus b squared should be the absolute value of cx. Since the logs are the same, the argument should be the same. And so my v squared is cx minus 4. And so my v of x will be the square root of the Alright, so is that our solution? No. Okay, we are looking for y. Right, so where's our substitution? Here. We use this to get y. Okay, so since that is v, then it means that cx minus 4 to the 1/2 power is equal to y over x. And so my y of x is just x times the absolute value of cx minus 4 to the 1/2 power. Okay. So here I've used my change of variable to get that. Any questions? Yes?
Can you clarify the last part?
This?
Yeah.
Okay, so here, the way we transform this equation to be separable is that we said let v be y by x. So now that we have found v, my v is y by x. And then I just solve for it.
Thank you.
Yes?
Why is the ln of 4 plus b squared become parentheses with the cx?
Because 4 plus v squared is always going to be positive.
But cx.
But we don't know x could be anything. Any other questions? All right. Now, of course, there's one thing that I have skipped over. This is not entirely correct. This is just one part of my solution. Okay. So notice that at this point in time, when I solve for v, I only consider the positive square root. But there are two possibilities for v. It could be the positive square root or the negative square root. Okay. So depending on your initial condition, you will either be taking the positive or the negative. So this is plus or minus. Right. Which means that that is plus or minus, and this is actually plus or minus. Depending on your initial condition. One of these will take precedence. Or you can leave it as an implicit solution, right? where you just say that, so since y is Vx, easier way to think about this. If you want to avoid the square root, so my v squared is going to be y squared over x squared from my substitution. So I can replace this with, and say that, oh, absolute value of cx minus 4 equals y squared over x squared. Right. And then I have y squared being equal to x squared times absolute value of cx minus 4. So that I don't assume that the function is either positive or negative. You know that's fine. Any questions? All right. So these are the major substitution methods that we're going to be working with. The Bernoulli equation, the case where you have a composition of a linear function, and the case where you have a composition of the rational function y of x. You know what to do in that case. All right. Now moving on to a different form of f of x, y that we can handle. The goal is still the same. The goal is to transform the equation into a form that we can directly integrate. This is always the story. Because we don't know anything else in how to reverse derivatives. It's the integration process. Okay? So that's always the idea. So consider, this is about exact differential equations. Consider, okay, so again, reminding you of the general form or the normal form. So we are still looking at equations of this type. Now, if my f of xy is minus mxy over nxy. So it's a rational function or a ratio of two multivariable functions. They need not be rational functions. So that my differential equation is of this form. What do I do? Now, n and m could be anything. So this could be a highly nonlinear problem. Or it could be that m is separable, n is separable, right? And then you can separate this out very nicely. Okay. But I want to think broadly. So is there a way, because at this point in time, if these guys are very weird, we can do direct integration, yeah? Because we have this in terms of x and y on that side. So can we make this in a form that can be directly integrated? All right. Now, if this is the derivative of y, then we know that the differential of y is minus mxy over nxy times the differential of this. Okay? And so I have nxy times the differential of y is minus mxy times the differential of x. If I send the differential of x and m to the other side, I have mxy dx plus nxy y equals 0. This is another way of stating the differential equation. This is the differential form, or the differential representation. because differential form would be something else. Okay, so we're going to tell the story from here. The method that we're going to be introducing is going to be based on this formulation of the differential equation and all that. But at least you know that this is where it came from. Okay, so this is not anything new. It's the same story, except that this lends itself more easily to the method I'm going to describe. All right. So as usual, we're going to make some assumptions about M and N. Okay. So let's assume that there exists some function I have abused the capital F, but capital F of xy such that the partial derivative of f with respect to x is exactly m, and the partial derivative of f with respect to y is exactly n. Let's assume that. Why are we assuming that? It will be evident in a minute. But let's say such a function exists. If that is true, then I can rewrite this in terms of the partials of f. And I have the partial of f with respect to x, dx, plus the partial of f with respect to y, dy, equals 0. Yes? Alternatively, I can write this as the partial of f plus the partial of y dy dx equals 0. Right? Now look at this very carefully. This is a function of two variables. This is the partial with respect to f and the partial with respect to y. Now, how would you construct this derivative, the total derivative of this function? Think back to part 3. If I wanted to find the total derivative of this with respect to x, what would I do? Multivariable function in x and y. Y is a function of x. I want to differentiate this function. Not the partial derivative, but the total derivative. Right. I'm going to differentiate the function with respect to the first argument, the partial derivative. Right. Multiply by the derivative of the first argument, and the derivative with respect to the second argument times the derivative of the second argument. Do you remember that? Somehow it's coming to you. Okay, so this will be the partial of f with respect to x times dx dx, which is 1. Sorry? Chain rule, yes. It's a chain rule. It's a chain rule over multiple arguments. Right? If it's a function of a single variable, then it's just 1. But if it's multiple variables, then you have to apply the chain rule to each argument. So this is plus the partial of f with respect to y times dy dx. So this is the expression for the total derivative with respect to x. And that is exactly what we have here. What does this mean? It means that if this assumption is true, then this differential equation is the same as saying that d dx of f of xy is 0. Right? Okay, now if the total derivative of f is 0, what does that say about f? It's a constant. So clearly, this function satisfies this differential equation for any constant c. Which means that this function satisfies that differential equation for any constant c. And it satisfies this differential equation for any constant c. In other words, if you can find a function whose partial derivative with respect to x and y corresponds to the coefficients of the differentials, you have found a solution to the differential equation. Period. If such a function exists, we say that this is an exact differential, or the differential equation is exact. Exact because it leads us to a total derivative. And you only have to solve by integrating, right? How do you go from here to here? You integrate that with respect to x, you integrate that with respect to x, and you get this. So again, we've come back to direct integration. We have transformed the differential equation into a form that we can directly integrate. Boom. Have application. Yes? Okay. So, the critical component of this method is finding this f. How do we get this f? If you have it, you have your solution. You have your general solution. This set is equal to a constant. Okay? All right. So we'll take an example. This is my example. Is it 5? What's it count? I think it's my example 5, but it's your example 4. Find a general solution for the ODE y cubed dx plus 3x y squared dy equals 0. Now, don't get worried about this. You know where this comes from. This is just the differential formulation of a normal form of effects of the differential equation. So we don't worry about that. It's not new. Okay. But the question then is there an f of x, y such that the partial with respect to x is y cubed and the partial with respect to y is 3x y squared? Does this function exist? Yes? xy cubed. So f of x, y is xy cubed. What does that mean? Well, it means that my general solution is xy cubed equals c. Because I already know that this function will satisfy this differential equation. You take the total derivative. Okay. Remember that the total derivative is just this. And it's equal to 0. So we are satisfying that differential equation. Okay. This is the total derivative. Because that's the partial with respect to x. That's the partial with respect to y. So it satisfies that differential. It's a two-step process. Find f. Oh, you have your solution. Okay. All right. Now, of course, a lot of the work. This was a very nice problem. You could easily look at it and say, oh, okay, this is how f of x should be y. Generally, it's not that straightforward to figure it out. So we need to look at a more reliable process for determining this f, so that you can always figure it out. So I'm going to take the same example, but I'm going to work this out slightly differently so that we can formulate a more reliable process. So let's go back. I think I can squeeze. So still on example 5, we have y cubed dx plus 3x y squared dy equals 0. Now my m of xy is y cubed my n of xy is 3xy squared. I want an f such that my partial with respect to x is y cubed and my partial with respect to y is 3xy squared. Okay, now, if this is a partial derivative with respect to x, and I want f of xy, what operation can I perform? Yes?
You would integrate
Yes, you would integrate assuming y is constant. That's a partial integration. You would integrate with respect to x assuming y is constant. That will give you f of xy. Okay, so if we do that, if I integrate with respect to x and this is a constant, then the integral is just x times the constant. So the integral of this is just going to be x, y cubed. Because y cubed is a constant. Right? It's just a constant. And so it must be true that if I take the partial with respect to y of this, I should get this. Okay. Now, there's another thing we have to bear in mind here. So this is true. This result, if I differentiate this partially, I won't get that. But what if I have, in addition to this, a function of y? Would it change my derivative? In other words, if you differentiate this partially with respect to x, do you still get that? Yes. Okay, so the integration constant in a partial integration is not necessarily a real number. It's just a function of the other variable. Okay, so doing this integration process just releases some function of y. We don't care what it is. It could be a constant, it could be a function of y. It's like a constant to us because we are doing a partial integration. Alright, so then if I differentiate this with respect to y, I should get that. And so my partial f partial y will be the partial of y of x y cubed plus g of y. Okay. Now here I'm going to get 3xy squared plus g prime of y. Because g is just a function of y, so that's actually a total derivative. And so from my assumption, 3xy squared plus g prime of y should be the same as my n of xy, which is 3xy squared. Now, what does that say about g prime of y? It's 0. And so my g prime of y is 0. So what can I say about g of y? It's constant, because this is a total derivative here. It's just a single variable. So that's a constant. And so my f of xy is just xy cubed plus c. And that is my general solution. Remember, this is what you predicted. Just by looking at it. And so by performing this series of partial integrations, you can always regenerate your f, if you are careful.
What's the general solution at the end of that?
Say that again?
What's the general solution at the end of that? X, y, cubed equals c.
Yes, that's the same thing. Because if I set this equal to a constant, the constants can just go to the right hand side. Right, if I set this f of xy equals to some d, then I have xy cubed equals d minus c, and that's just another constant e. So it doesn't actually change my result in any way. Remember, the constant will be determined by initial conditions. Did I answer the question?
Yeah, no, I got it.
You got it? Okay. Okay, so this was a trivial one. Let's take a more interesting example where we will probably have no idea what the f of x would be. So this is my example 6, and it's also your example 6. So solve the differential equation 6xy minus y cubed dx plus 4y plus 3x squared minus 3xy squared dy equals 0. Okay. So it may not be entirely obvious what functions partial derivative with respect to x will give me that, and partial with respect to y will give me that. And so I can proceed as usual that I want f of x, y such that the partial with respect to x is 6xy minus y cubed, and the partial with respect to y is 4y plus 3x squared minus 3xy squared. That's what I want. Okay. So for this to be true, then my f of x, y has to be the partial integral of that with respect to x. So if I'm thinking of y's as constant, and I'm integrating this with respect to x, I have 6x squared over 2y minus xy cubed. Plus a constant, which is just a function of y. Okay. Now if I compare this to that, of course, let me first of all differentiate partially with respect to y before I can compare to that. So this is 3x squared minus 3xy squared plus g prime of y. And now if I compare these two, I have a 3x squared and a 3x squared. I have a minus xy squared and a minus xy squared. And I have a g prime of y, which must be 4y, for these two things to be identical. And so g prime of y has to be 4y, which means that my g of y is 4y squared over 2, which is 2y squared. So what does that mean? It means that my f of xy is 3x squared y minus xy cubed plus 2y squared. And so the general solution is that set to a constant, 3x squared y minus xy cubed plus 2y squared equal to the constants. That's my general solution. This comes from setting these guys equal to each other and comparing terms. Okay? Now, it is not every equation in differential form that is exact. In other words, you are not guaranteed that once you write the differential equation in this form that you will be able to find such an f. Okay? And so before you go ahead doing these partial integrations to find the f, you want to be able to, you want to be sure that it exists. So on Monday we'll talk about when do we know that a differential equation is exact? Very quickly, before we start doing these partial integrations to compare this.
Which lecture should we go over for quiz?
Up to this point. So you do the practice problems up to